Hi, I hope that you are doing great. In this video, I'm going to solve the problems related to Lecture 13, Factoring Polynomials, Part 3. Below the video, you will find 5 links. The first link is the link to the PDF file containing the problems I'm going to solve in this video. The second link is the link to the PDF file of these notes that right now you can see them in front of you. That in this video I'm going to use them to present the lecture. In this file, the solutions that I will present in this video are not included. I use iPad Pro with Apple Pencil together with GoodNotes 5 application to produce these videos. The content of the third link is essentially the same as the second one, except that this one is the GoodNotes file. I strongly recommend you to have one of these available when watching this video. If you have access to a tablet with GoodNotes installed on it, then you can use the third link to download the file directly to your tablet. Otherwise, you can use the second link to download the PDF version of the notes and then print them. The fourth link is the link to the PDF file of these notes. This time, all the solutions that will be presented by the end of this video are included. Finally, the fifth link is the GoodNotes version of these notes, including solutions. Okay, now the first question, part A. Factorize the following polynomials. So there are 4 polynomials here. I want to factorize them for you. So let us do it one by one. So number 1, what can I do? Here I can take these two together and I can take these two together, yes? From the first group I can factor 3a out, so it becomes 3a, and then x plus y is left. And from the second group I can factor minus b out, then x plus y is left. So this is a successful grouping because now you can immediately see that a common factor emerges. And I can pull this one out, so it becomes x plus y times 3a minus b. So that is the final answer to this factorization. Okay, so let us go to number 2. Yes. So number 2. Let me write it here. Okay, so if you look here, probably you can find that, yes, first of all, there is a common factor to all of these terms, and that is 2. So the first thing that I have to do, I factor 2 out first. Okay, so I will factor 2 out. Then what is left is 4a to the 3 minus 2a plus 2a squared, then minus 1. Yes. Now I start grouping them together. Yes, for example, I can take this one and this one together, and I can take these two together. Okay, so then what happens? I will have 2 times, I factor 2a out, and then I will have 2a squared minus 1, and then I can put 2a squared minus 1 together. Yes, so let us check that. So you see, if I multiply this 2a back, it becomes 4a cubed, which is this one, and then it becomes minus 2a, which is this one, and I haven't done essentially anything with these two terms. Yes, so then this is also a good grouping because now you can see that a common factor emerges. So immediately I can pull it out, so it becomes 2, and 2a squared minus 1, I pull it out. Then what is left from the first one, you see 2a squared minus a is pulled out. So from this one, 2a is left, so I put 2a here. And from this one, because we have to divide by what we get out, bring out, it becomes 1. So the answer becomes 2a plus 1. and we cannot go more than that. So this is the solution to this problem. Okay, now let us go to number 3 here. So number 3, let us see which one is suitable. It's very clear, yeah? So if I take these two together, and if I take these two together, for example, it probably will work. Okay, so between the first group, I factor b squared out, so it becomes equal to b squared y minus 1. And between the second group, I will take minus a squared out, yes, because I want to have y minus 1 appearing. Otherwise, it would be 1 minus y, and then it would be with the wrong sign. So I took minus a squared out. Okay, now this is good, yes, because now you see that y minus 1 is indeed the common factor, so I can pull it out. Then I am left with b squared minus a squared. Of course, this is in factorized form because it's a product, but it's not complete because b squared minus a squared is the difference of two complete squares, and I have used the conjugate rule, yes? So then what happens? It becomes y minus 1, and then I have b minus a, b plus a. And that would be the answer to this one. Okay? So now let us go to number 4. So what can we do in number 4? I think if you have already thought about the problems, you can see that I can take these two, because these two will actually give me a conjugate pattern, and then I can factorize these two, and then 2x minus 3y will be the common factor, yes? So just let us write them here. So let me write them in this form, in brackets. So I will have 4x squared minus 9y squared, and then what is left for me is 2x and minus 3y. So I will write them in another pair of brackets. So it is 2x minus 3y. But then you immediately see that this one can be factorized using a conjugate pattern. That's the difference of two complete squares, yes? So then it becomes 2x minus 3y times 2x plus 3y, and then I will have plus 2x minus 3y. Now you immediately see that this grouping was successful because now I have this common factor. So I can pull it out, so then it becomes 2x minus 3y. What is left from the first one is 2x plus 3y, and what is left from the second one is just plus 1. But no one uses extra brackets if they are not needed, so let us remove them because they are not actually needed in this case, yes? So then it becomes 2x plus 3y, and I have 1 at the end. So that is also the solution of part 4. Good. Let us go to the next page. So number 5, let us see what is suitable. I hope that you have already thought about the problems. If you haven't done that, I really recommend you to pause the video right now and try to think about the problems yourself. You will not learn mathematics just by watching the videos. You have to learn it in an active way, yes? Okay, so here I would say that a good strategy is to take these two, and then I can take these 3 together. Okay? And by the way, I have already thought about the problems before doing this, a little bit at least. The reason is that sometimes you have to do some trial and errors. The reason that you see that I immediately go and group them in a correct form because I have done a little bit of studying before presenting these lectures, yes. Okay, and so this is why I'm saying that don't think that I go directly to the correct solution, even though I have a lot of experience of these things right now, but still I have to do sometimes some trial and error. Okay, so it is inevitable sometimes, so you need to do it more or less yourself. Okay, so I will factor x6 out from the first two. You see, I decided to group them together. They have a factor of x to the power of 6 in common. And then there is nothing in common here, but if I factor minus sign out, then it will be a quadratic pattern. Okay, so let us see how it goes. I take x6 out from the first one, from the first group. It becomes x squared minus 1. And as I told you, take a negative sign out. It becomes x to the 4 minus 2x squared positive 1. Yes? If you multiply this negative sign inside, this one becomes negative as it should be. This one becomes positive as it should be. And finally, the last one becomes negative as it should be. Okay? Now, what is the benefit of this? Let us continue. This becomes x to the 6, x squared minus 1. But this second one is a quadratic pattern. So if I collect the terms, it becomes x squared minus 1 to the 2. Let us check it again. The first 1 to the 2 gives you x4. 2 times the first one times the second one gives you exactly this term. And finally, this 1 to the 2 will give you positive 1. Yes? It's a good factorization. It's a good grouping. Why? Because now you can see that I have a factor in common. This one is actually x squared minus 1 times x squared minus 1. So you immediately see that this is a common factor between these two, so I can pull it out. Yes, so then it becomes x squared minus 1. What is left from the first one is x to the 6, and what is left from the second one is x squared minus 1. Yes. So let us simplify this a little bit. Then this becomes x squared minus 1. The second one becomes x to the 6 minus x to the 2 plus 1. Yes. And then of course the first factor can be simplified, it can be factorized more. So it becomes x minus 1, x plus 1, and then I will have x to the 6 minus x to the 2 plus 1. Okay, so that is also a factorization of this polynomial. Now let us go to number 6. So in number 6, hopefully you learned from the previous video what we have to do here, yes? So this becomes equal to, instead of a4, I write 2a4 and then I subtract a4 at the end to compensate for this addition of a4. So this becomes a to this 8 plus 2a4 plus 1 minus a4. Yes, I hope that you appreciate this equality. Positive 2a4 negative a4 is exactly a4. A to the power of 8 is here, 1 is here, so nothing is changed. But what is the benefit of that? If you have watched the previous video, you can immediately realize that this can be written as a to the 4 plus 1 to the 2 minus a to the 4. Yes. Let us double check. This one to the power of 2 is the first one to the power of 2, which is this one. 2 times the first one times the second one, which is exactly this one, and finally the second one to the 2, which is this one. Yes, so what I have written is completely correct. But what is the benefit of that? Because now you see that this is the difference of two complete squares. A to the 4 has another name. It's a to the power of 2 to the power of 2. So a to the 4 is a complete square. This one is also a complete square. So I can use the conjugate rule to factorize this polynomial. So then it becomes a to the 4 plus 1, the square root of the first one, minus the square root of the second one, multiplied by the square root of the first one, plus the square root of the second one. Okay? So let me organize this a little bit. So it becomes a to the 4 minus a squared plus 1. And the second one becomes a to the 4 plus a squared plus 1. Yes. But I can use the same trick, more or less the same trick that I used here, and I can still factorize this expression more, but not this one, yes? So what I do, let me just write this part here. Let me change my color. Let me write this one here. A to the 4 plus a to the 2 plus 1 can be written exactly the same way. Can be treated exactly the same way. So I can write it as 2a squared plus 1, and then I will write minus a squared at the end. Okay, so then again I can collect the term, so it becomes a squared plus 1 to the 2 minus a squared. Why? The first one to the 2 times the first one times the second one, and the second one to the 2. Okay, so again this is the difference of two complete squares, so I can write the square root of the first one minus the square root of the second one, and the square root of the first one plus the square root of the second one. And if I reorganize it, it becomes a squared minus a plus 1. Then I will have a squared plus a plus 1. Yes, but this is, I need to replace this here instead of this. Yes, so finally my final answer is equal to, I have this one, and instead of this I put this product. Yes, so what I get is, this is a to the 4 minus a to the 2 plus 1, then I have a squared minus a plus 1, then I will have a squared plus a plus 1. That would be my final answer to this problem. Okay, you might wonder, how do I know that I can, for example, cannot factorize this more? Or, for example, even in the previous problem, how should I know that I cannot continue and factorize this polynomial even more? Okay, um, of course, this polynomial and that polynomial, you can factorize them if you want to work on the complex numbers. Okay, but how we should know that these polynomials cannot be factorized on the domain of integers? This is the content of my next video actually. There I will teach you about how you more or less know about these things. And so if I want to just briefly talk about that, is that this polynomial, if this, I will show in that video that, in the next video, that if this polynomial is going to be factorized on the set of integers, because this coefficient is 1, and then the integer roots of this polynomial, if they exist actually, should be factors of 1. So it means that the factors should be positive or negative 1. But it is very easy to check that none of them are actually the root of this equation. If I put 1 here, 1 to the 6 minus 1 to the 2 becomes 0, but then it becomes 1. It is not 0. And if I put minus 1, the same. Okay? So if you want to answer these questions in more details, if you want to understand them, you need to watch the next video that I'm working now on it, and I probably publish it by next day. Okay, so let us go to problem number 7 now. Okay, so problem number 7. So what is a good combination here? Okay, so if you look between these two, I can factor a4 out, and between these two I can factor negative 16 out. So what is left is here. I can write it in this form: a to the 4, a to the 3 plus 1. I factor minus 16 out from the second group. It becomes a to the 3 plus 1 again. Yes, this is a good grouping, yes, because this factor is now in common. So I pull it out, so it becomes a to the 3 plus 1, and then I have a to the 4 minus 16. Of course, this is in product form, but it is far from being complete, yes, because this one is a to the 3 plus 1 to the 3. This is the sum of two complete cubes. We have an identity for that. And this is the difference of two complete squares. So we have to continue, yes? So for the first one, I can write a plus 1. Then I would write the square of the first one, the product of these two with the opposite sign, and the second one to the 2. For the second term here, for the second factor, I can use the conjugate pattern. So it becomes a squared minus 4 times a squared plus 4. Still, it's not complete because this one can be factorized more using the conjugate pattern once more. So then it becomes a plus 1, a squared minus a plus 1, and then I will have a minus 2, a plus 2, and then I have finally a squared plus 4. So that would be the solution to this problem. Okay, number 8 is a little bit more tricky. I spent a little bit of time doing some trial and error before start recording this video. So let us share my final solution with you. So what I did is this. I start breaking these terms. I started breaking this term and that term, but it was not that easy to guess which is which, so I should break it into which terms. But now I can see that, so let me write it here for you. So I wrote a to the 3. Instead of 3a squared, I wrote a to the power of 2. Yeah, so let me write 2a squared first. 2a squared plus a squared. So instead of this middle term, this term, I wrote 2a squared plus a squared. And then instead of 5a, I wrote 3a plus a, and then I have 6 at the end. Okay, hopefully now you can see why this is good, because I can factor a squared oh sorry, I made a mistake here. I made a mistake. This is not a, this is 2a. Yes, sorry. Okay, 2a, because that was 5a, so this is 3a plus 2a, which becomes 5a. Now everything works fine. So now I will take this one with this one. I will take this one with this one. And finally, I will take this one with that one. Okay, let us see how it goes. This becomes equal to, I have a squared. Between these two, I can factor a squared out, so it becomes a plus 2. Between these two, I can factor a out, so it becomes a times a plus 2. And between these two, I can factor 3 out. And then you see that this is actually successful, yes, because now this common factor emerges. So then I can pull it out. So then it becomes a plus 2. Then what is left for me is a squared plus a plus 3. Yes. And if I want to factorize it on the set of integers, I might ask myself, because now this is a quadratic polynomial, if I want to succeed to factorize that, so I have to put a here and there, and then I should ask myself, I need two numbers whose sum is 1 and the product is 3. Of course, I want to work in the realm of integers. Okay, but the product of integers to become 3 are only 1 and 3, or -1 and -3, but in no way they can add up to +1. So it means that this is the end of the problem. Yes. So I will keep it here. This is the answer to this problem. Okay, now let us go to the, okay, we have done everything on this page, so let us go to the next page. Of course, the questions are a little bit more tricky here. Okay. Yes, let us see what we can do here. Number 9. Okay, so here in number 9, I broke this 12 in a way that it contains these numbers somehow, these coefficients. Okay, how? So I wrote it in this form. A to the 4 plus 2a to the 3 minus 7a to the 2 plus minus 8a instead of 12, I write a plus 7 minus 2 minus 1. Yes, let us see. 8 plus 7 is 15, minus 2 is 13, minus 1 is 12. So what I have written here is indeed 12. But what motivated me to do this? Because I saw that I can factor 8, for example, here, 7 here, 2 here, and then I can combine this one with that one. So let us do it in this form. So it becomes equal to a to the 4 minus 1. I combine this one and that one. Between these two, I can factor 2 out, so it becomes 2a to the power of 3 minus 1. Yes. Between these two, I factor minus 7 out, because I want to have a squared first with positive sign. So I will take minus 7 out. It becomes a squared minus 1. And then finally, between these two, I can factor minus 8 out again. Yes, so what is left is 8a minus 1. So let me repeat. I took this one with the last one. I took this one with this one with this, and finally this one with this. Okay, but now let us see how it goes. A to the 4, still you might say that I don't have any term in common. You are right. But then if you look a little bit ahead, you can immediately see that you can have an a minus 1 coming out from here, from here, from here, and that's also a minus 1. Yes? So let us factorize this. So a to the 4 minus 1 can be factorized by the conjugate rule. A squared minus 1, a squared plus 1. The second one can be factorized by using the difference of two complete cubes. So the answer becomes the cubic root of the first one minus the cubic root of the second one, and then you have to write the first one to the 2, the product of them with the opposite sign, and the second one to the 2. The third one, so if you don't mind, let me write it's here. So the third one is minus 7. I can factor a minus 1, a plus 1. Yes, and then I will have minus 8a minus 1. Okay, but if you don't mind, let me just do this one here, because of course you see that I have a minus 1 here, 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 so I can pull it out. The only obstacle is that this is a squared minus 1, but that I can easily solve that problem, yes, because this one on its own is a minus 1, a plus 1. Now look, this term has a minus 1. A minus 1, a minus 1, a minus 1. So all of them now share a factor of a minus 1 so that it can be pulled out. Yes. So what happens now? This becomes equal to a minus a1. So let us see what is left. You see, a minus 1 is pulled out. A plus 1 and a squared plus 1 are left. So a plus 1, a squared plus 1 are left. Okay, then you have a minus 1 pulled out from here, 2, and this one is left. So it becomes 2 a squared plus a plus 1. And then here a minus 1 is pulled out, so minus 7 times a plus 1 is left. So it becomes minus 7 a plus 1. And finally I pulled a minus 1 out, so what is left for me is minus 8. Okay, this is already in factorized form. It's a product now, product of these two. But I told you, you will never leave this factor like that, because it might happen that if I simplify this factor, then I can still continue the factorization. Yes, so let us just continue. So I would write a minus 1 here. To simplify this, I have to expand everything, because now my goal is simplification of this factor. Okay, so I multiply a times a squared is a cubed, then it becomes a, then it becomes a squared and plus 1. And then I multiply 2 inside, so 2a squared plus 2a plus 2. And then I will have minus 7a minus 7 minus 8. Okay? So then it becomes a minus 1. So let us simplify. A3, no similar terms, yes? But now a squared and 2a squared are similar. So if I add them, it becomes 3a squared. Yes? And then you see that I have a, 2a, 3a, minus 7a is minus 4a. So let me write minus 4a. And finally, if you see, I have minus 14, yes? So it is 1, no, sorry, 1 and 2 is 3. So let me write them in this form. 1 and 2 is 3. Minus 7 is minus 4, minus 12. So that's minus 12 now. Okay. But then it is not that hard to see that this can still be factorized. Could you see that? Yes. Here I can combine this one with that one, and I can group these two together. Why? So let us continue. It becomes a minus 1. Then I will have a squared pulled out from the first group. Then I will have a plus 2 left, a plus 3 left, sorry. And then from the second one, I can factor a minus 4 out. Then I will have a plus 3 left. And you see, this was good, yes, because again, I have a plus 3. I can pull a plus 3 out. Then what is left? A plus 3, I pull it out. Then a squared is left from here, minus 4 is left from here. Yes, but this is not still complete because the last one can be factorized even more using the conjugate pattern. So then it becomes a minus 1, a plus 3, a minus 2, a plus 2. So finally, this is the full factorization of this polynomial. Hopefully I can fit everything here. So number 10, let us see what we can do. In number 10, I want to take this one with that one. I want to pull AB out, so the factor that will emerge is A minus B somehow. So I want to make A minus B available from the other ones as well, yes? So then it will motivate me to factor these two. I want to group these two together. Then I have to group these two together. Yes. Okay, so if you don't mind, let me take this one with me somehow. This is a picture, I cannot move it around. Okay, so let me just do it here for you. So number 10, between these two, I factor AB out, yes? So I factor AB out. The first one, from the first one, B is left, and from the second one, minus A is left, yes? Between these two, I factor C squared out, then the same thing actually is left. That's B from the second one and minus A from the first one. And in the last one, this is the last one. In the last one, I factor C out, so then what is left? I factor minus C out this time, okay? So it becomes minus C, then it becomes positive B squared, negative A squared, yes? Minus C times B squared is minus B squared C. Minus C times minus A squared becomes positive A squared C. And hopefully you see what is the benefit of doing that is I can go one step further, so it becomes AB, B minus A, and then I will have C squared, B minus A, Then I will have minus c. B squared minus a squared can be factorized b minus a, b plus a using the conjugate pattern, yes? And now you see that b minus a actually emerges. So I can pull it out. So then it becomes b minus a, and then ab is left from the first one, c squared is left from the second one, and then minus c times b plus a is left from the last one. You see, b minus a is pulled out, so ab is left here, positive c squared is left here, b minus a is pulled out, so minus c times b plus a is left. Again, I have to simplify the second factor because it might happen that I can still continue. And this becomes c squared minus cb plus minus ca. Now I want to factorize things, so let us group them again. So which is suitable here? You can immediately see that b is, yes, I can take this one, for example, with that one, and I can take these together, yes. So I will continue. I will write b minus a, then I can pull b out from the first group. It becomes a minus c, and I want to make a minus c again, so it motivates me to pull minus c, not c out. Then it becomes a minus c exactly, yes. So you see, I pulled minus c out. Minus c times a is minus ca. Minus c times minus a is positive c squared. Everything is okay. Now I have this common factor that I need. Yes, so I will take it as b minus a minus c. I pull it out, then b minus c is left. When I pull this out, b is left, minus c is left. And that's the final answer. Of course, you can play around with the negative signs if you want. For example, I don't know, I prefer to this instead of b minus a, I want to have it a minus b, so I have an extra factor of minus sign. Then I would write b minus c as it is, but the minus sign that I pulled out from here, I multiplied here, then it becomes c minus a. So it doesn't matter, of course, both of them are actually indeed correct. Okay. So now we need to go to problem number, let us see if I hope that I can fit everything here, yes. Okay, so let us go to problem number 11, and then let me try to draw some border here, so not to mix things up. Yeah, so I can just here, because I want to keep these in front of you. Okay, the trick for the next one is actually interesting. So problem number 11, yes. So problem number 11, I do this. What I do, I break the, I will break the, let me think, the middle one. Yes, so let me see. So I would write it in this form. I would write a to the 4 plus b to the 4 plus c to the 4. And then I will write minus 2a squared b squared, that's good. And then I will write minus 2a squared c squared. But instead of minus 2b squared c squared, I would write positive 2b squared c squared, but to compensate for that I need to subtract 4b squared c squared. Yes? Okay, so let me convince you that what I have done is indeed correct, yes? These three terms are exactly these three terms and nothing changed. These two terms are exactly these two this term and that term, yes? But then instead of minus 2b squared c squared, I have written positive 2b squared c squared minus 4b squared c squared. That's exactly the same thing. But what is the benefit of doing that is that if you realize I can group all these together now. Do you remember which identity it is? Yes. So this becomes this identity. Let me change my color. So a squared plus b squared plus c squared, sorry, these are minus signs, minus b squared minus c squared to the 2. Let us double check. If you remember, this identity to the power of 2 is the first one to the 2, which is this one, the second one to the 2, which positive b4, the third one to the 2 is positive c4, 2 times the first one times the second one is the negative 2a squared b squared, 2 times the first one times the third one is negative 2a squared c squared, and then 2 times the second one times the third one becomes positive. You see? It becomes positive 2b squared c squared. So what I have written here is exactly this expression, and then I have minus 4b squared c squared left. And of course there is another name for that, and that is 2bc to the power of 2. Okay? But then it becomes very clear, this is now the difference of two complete squares. So what can I do? I can use the conjugate rule. So it becomes the square root of the first one minus the square root of the second one times the square root of the first one plus the square root of the second one. Yes? But now the trick is to write it in this form. Instead of writing minus minus minus, I can pull a minus sign out, so it becomes a squared minus b squared plus c squared plus 2bc. And in the second one I can do the same thing. I can write it minus, so I am pulling a minus sign from these three out. The first two become positive, the last one becomes negative, yes? So then it becomes minus b squared plus c squared minus 2bc. And then I have to close it. And then I can write it in this form. I can write it as a squared, but now this is a quadratic pattern, this is also a quadratic pattern, so I can write b plus c to the 2, and then I will have a squared minus b minus c to the 2. Okay, very good. Now again I have two conjugate patterns. Why? The difference of two complete squares, the difference of two complete squares. So what I do, I would write it in this form. The square root of the first one minus the square root of the second one, square root of the first one positive square root of the second one, and the same thing for the second factor. The square root of the first one minus the square root of the second one, the square root of the first one plus the square root of the second one. This is minus. Okay, but let us remove the extra brackets, not unnecessary brackets. So I would write a minus b minus c. The next one is a plus b plus c. The next one is a minus b plus c. And the next one is a plus b minus c. Yes, so this is my final answer to this problem number 11. Sorry for they are actually crammed inside each other, but hopefully you can understand what's going on. And I need some space for the last one, so if you don't mind, let me make it a little bit smaller to write it here, and then I can make the video a little bit bigger again. So let me draw a border here we don't need it, and then I would write this one here for you. So this is x to the 4 plus x to the 2 plus 5 to the 2 minus 32x to the 4 minus 32x to the 2 plus 15. Yes. Okay. Now we can make the video bigger and we can concentrate here. So that is the expression that I want to factorize. So what I did for this case is I wrote it in this way. Motivated by this expression, you see, if I factor minus 32 out from these two, I will get x to the power of 4 plus x to the power of 2. Yes. So I did it in this way. But I have an extra factor of 5 here. So I did it like this. So I would write x to the 4 plus x to the 2 plus 5 to the 2. Between these two, I factor minus 32 out. The first one gives me x to the 4, the second one gives me positive x to the 2. I myself put a 5 here. Why? Because I need a 5 here. But of course, putting a 5 here, this 5 will be multiplied by this. It will give you minus 160. So it means that I am subtracting minus 160. I cannot just do that unless I add 160 to it. And then of course you see that I have an extra 15. I put that 15 in. Let us wait, let us understand what's going on. This term here is exactly this, no changes. Minus 32 times x4 is exactly this one. Minus 32 times x squared is exactly this one. But let us see. Minus 32 times 5 is minus 160. Plus 160 is totally gone. And what is left is 15. So this equality is indeed valid. And then if you don't mind, let me just clean them here instead of writing everything down. 160 plus 15 is 175. Yes. So let me clean this and write 175 instead. Plus 175. Okay. Now look, if you take this x to the 4 plus x to the 2 plus 5, let us take it, for example, capital X. Then the expression is x to the 4, x to the 2 minus 32x plus 175. Yes. Okay, so this means that I want to factorize this expression now. I want to factorize this expression. Okay. If possible, might be you can see that so you want two numbers. Let us see, because I don't want to use the calculator as much as possible. So I want to ask myself if I can succeed to factorize this using the common term identity. So I have to put an x here and x here. Then I will ask myself, I need two numbers whose product is negative 32. The sum is negative 32 and the product is 175. So the numbers are big, so I would do like this. I immediately realize that 175 is divisible by 5, so I divide it by 5. So if I divide it by 5, what will happen? It becomes 35, yes? So it is 5 times 35. So this is 5 times 35, yes? And then this is 5 times 7 times 5. And then you immediately see it becomes clear, because it is 7 times 25, by the way. Yes, I could realize that. 725 is very good. They are good numbers. Why? Because they have a relation with 32. If I add 7 and 25, it becomes exactly 32. But I need to adjust the signs. The product is positive. So it means that either both of them are positive or both of them are negative, but because the sum is supposed to be negative, I have to choose both of them to be negative, yes? So what happens? I will have x minus 25 and I will have x minus 7. Yes, let us double check. These two numbers, the sum of these two numbers is minus 32, and the product of these two numbers, 7 times 25, is exactly 125. 175. Okay, and then I can put this back here, and I can put this back here. Of course, this is already in product form, but it might happen that we can still factorize more. Yes, so this becomes x to the 4 plus x to the 2 plus 5. I put it instead of x, but minus 25. Yes, and then I will have x to the 2, x to the 4 plus x to the 2 plus 5 minus 7. So what I did, I replaced this x with this one here, and then I have minus 25, which I wrote here. And I replace this x again by this expression. I have minus 7 here, I put it here. So let me simplify each factor now. And if you don't mind, let me clean this. We don't need this anymore. Okay, thank you. Yeah, So what happens is x to the 4 plus x to the 2 minus 20, and then I will have x to the 4 plus x to the 2 minus 2. I hope that you can immediately realize what's going on. Each one of them can still be factorized, yes, but this one here, x squared is playing the role of the common term in both of them. So I will write, I open two pairs of brackets, I put x squared here and here. This is for this one. And I open another two pairs of brackets, x squared, x squared. This is for this one. Here, I ask myself, I need two numbers whose sum is positive 1 and its product is negative 20. This is easy to guess, yes? One of them is positive 5, so I put it here. The other one is negative 4. Let us double check. 5 minus 4 is indeed plus 1, and the product is minus 20. That's completely correct. And here, I want to ask myself, I need two numbers whose sum is positive 1 and its product is negative 2. It's also simple, yes? So one of them is positive 2 and negative 1. Yes? Yes, that's correct. But then you see that these two again are conjugate patterns. So it was a little bit lengthy, yes? So it becomes x squared plus 5. The next one becomes x minus 2, x plus 2 using the conjugate pattern. And the next one is x squared plus 2. And the last one is x minus 1, x plus 1, again by the conjugate pattern. So that is the fully factorized form of this polynomial. Okay, so this is, by the way, problem 12. So let me write this here. So that's problem 12. Okay, now let us go to the next problem. Okay. Okay, so this is the problem that I called it challenging. And I have, of course, given you the hint. Otherwise, it might be very hard. You need to do a lot of trials and errors to be able to discover the pattern. But I think that now using these things that I have provided, these hints, and then the experience that you have got so far, this problem is not that hard to solve. Okay, so let us just follow exactly what I have provided as a hint. I have mentioned that expand this polynomial and use these two facts. First of all, by the way, these two facts are correct, yes? 2a squared b minus a squared b is indeed a squared b, and 2ab squared minus ab squared is indeed ab squared. Okay. Okay, so I would expand, as I mentioned. So expand means I multiply this here, here, and then there. Okay, so this becomes ab squared plus ac squared minus a cubed. Then I will have bc squared plus ba squared minus b cubed. And then ca squared cb squared minus c cubed minus 2abc. Yes? But now, look, I have told you that it's better to do this. So instead of ab squared here, I use this. And instead of a squared b, which appears here actually, this is ba squared. Another name for that is a squared b. So here, I use this. And here, I will use this. Okay? And then I will copy and paste every other term. So then it becomes equal. Instead of that one, I would write 2ab squared minus ab squared. Then I will copy paste ac squared minus a3 plus bc squared. And then for the next one, I would write 2a squared b minus a squared b. And then I copy paste the rest. Yes. Okay. Now you see this one has a factor of 2. This one has also a factor of 2, and the last one has also a factor of 2. But of course, we have more common factors in principle between this and this one and that one. So let me change the color here. So between this one and the last one, I can factor 2ab out. Yes. So what's left for me? It becomes 2ab From this term, if I pull 2ab out, only a is left, so let me write it here. And from this one, when I pull 2ab out, b is left, positive b is left. And finally, from this term, if I put 2ab out, negative c is left. Yes. Okay. Now let us try to find others so that in a way I will be motivated by this. My goal is to be able to group other terms and in a way that I can have this or these as a common factor. Okay. Okay, so you immediately probably realize that a good idea is to take these together. So I will take minus a cubed, I will take minus a squared b, and finally this one. All of them share a factor of a squared. Because I want to have positive a, positive b, and negative c, so this means that I have to pull out a negative a squared. Yes, so I will pull out a negative a squared. Then let us see what happens. From this one, I pulled negative a squared out, so what is left for me is exactly a. And from this term, I pulled negative a squared out, so what is left for me is just positive b. And finally, from this term, I pulled negative a squared out. It was positive, so now it becomes negative. So that's a good thing, yes, because now you see this factor is exactly the same factor as here. Okay, so let us see what is left now. Okay, so here I can do the same thing for negative b squared. So how? I will take this one and I will take, so this one and this one. Yes, I factored negative b squared out. Let us see. Negative b squared. So here I have negative ab squared. Negative b squared is pulled out, so positive a is left for me. Okay? And then from here, I pulled minus b squared out, so positive b is left for me. And finally, from here, I pulled negative b squared out, so minus c is left for me. Okay? And then what is left now? This term and this term and only this term. These are left. But this is good because all of them now share a factor of c squared, you see. I can factor c squared out. Then from the first term here, a is left. From here, positive b is left. And finally here, negative c is left. So it's a plus b negative c. It's good. Now you see that this factor is a common factor to all the terms. So what I can do, I can pull it out. So what is left? I pull this out, 2ab is left, so I write 2ab. I pull this out, negative a squared is left, so I put negative a squared. I pull this out, negative b squared is left, and finally I pull this out, positive c squared is left. So I will write this for you. Yes, 2ab minus a squared minus b squared plus c squared. Yes, so it becomes 2ab minus a squared minus b squared plus c squared. Okay, so this is already factorized. But I can continue more, yes? You have experience for this type in the previous problem, yes? So what can I do? I can write it in this way. I can write it as a plus b plus minus c. Here, I would write c squared first. And between these three, I pull a negative sign out. So it becomes a squared negative 2ab plus b squared. You have enough experience. This is why I'm not explaining so much here now. If you have already watched the videos for these things, you are actually very you feel very comfortable. Okay, now why I did this? Because now you can immediately see that the second one is actually a quadratic pattern, so I can write it as a minus b to the 2. Yes, the first one to the 2 gives me this, 2 times the first one times the second one, and then finally the second one to the 2. But now this is the difference of two complete squares, and that I can use the conjugate rule. So this becomes a plus b minus c, and then it becomes c, the square root of the first one minus the square root of the second one, and the square root of the first one plus the square root of the second one. But we don't need extra brackets, so let us remove them by doing necessary changes. So it becomes c minus a plus b, and then the other one becomes c plus a minus b. Yes, so that is the factorized form of this expression. Okay? Yes, so now let us go to the last problem. I also called this challenging, but I didn't provide you with any kinds of hints. And the reason is that even though this might be a challenging problem, but if you are following my videos, in the previous set of problems you had some similar idea. So I want to make sure that you really understand the ideas behind the problems, and then you can use them in a different problem which are similar. Yes, in a different which is similar. Okay, so what should I do? I don't know, could you guess what to do or not, but based on the previous experience, it might not be that hard to introduce some new variables. I will define, so I would write it like this. So I would say let 2 to the power of x be equal to a, and 3 to the power of x be equal to b. Okay, then I will try to write this expression in terms of a and b. Yes, so what can I do? 2 to the power of x, so let me write it in this form as 8 to the power of x is 2 to the power of 3 to the power of x. But you know that I can write it as 2 to the power of x to the power of 3. So if I use this substitution, then it becomes a to the 3. The same thing happens for 27, yes? If I have 27 to the power of x, 27 is 3 to the 3, and then raised to power x, but I can interchange the exponents, so I can write 3 to the x to the power of 3. And then if I substitute this here, then it becomes b to the 3, yes? Okay. So what can I conclude is that the numerator 8 to the power of x plus 27 to the power of x can be written as a to the power of 3 plus b to the power of 3. Yes, so let us keep it. But what can I do for 12 to the power of x? Yes, 12 to the power of x, instead of 12, I can write 2 to the power of 2 times 3, and then I have to the power of x. Yes, why? 2 to the power of 2 is 4, times 3 is 12, so I have 12, and then I have this power of x, this exponent of x. So, and then I have a rule, so you know the rule. If I have, let me write it with different letters. So if I have alpha, for example, beta to some power n, then I can write alpha to power n times beta to power n. Yes, so I can immediately write this according to that rule, 2 to the power of 2 to the power of x multiplied by 3 to the power of x. But again, I can use the same trick. I can interchange these two exponents. So it becomes 2 to the x to the 2 times 3 to the x. But look, 2 to the power of x is just a, 3 to the power of x is just b. So I can write a to the 2 times b. And then the next one is 18 to the power of x, the same trick. So 18 to the power of x is equal to, instead of 18, I can write 2 times 3 to the power of 2 this time, and then to the power of x. 3 to the power of 2 is 9. 9 times 2 is 18, and then x is just x. And again, I use the same formula here, and I would write 2 to the power of x multiplied by 3 to the power of 2 to the power of x. Again, I can interchange the exponents, and I would write 2 to the power of x times 3 to the power of x to the power of 2. And then, you see, 2 to the power of x is a, 3 to the power of x is b. So 2 to the power of x is a, 3 to the power of x is b, but I have b to the power of 2. So it's b to the power of 2. So therefore, from here, we can conclude that the denominator is the sum of these two. 12 to the power of x, 18 to the power of x. So 12 to the power of x is this, 18 to the power of x is this. So I add them together. So 12 to the power of x plus 18 to the power of x is equal to a squared b plus ab squared. Yes? Good. But then what was my equation? The equation was this expression. Okay, so let me make it smaller to be able to write this in front of your eyes. So the equation is 8 to the power of x, 27 to the power of x, and then 12 to the power of x plus 18 to the power of x is 7 over 6. Okay? Now, what can I do? This implies that instead of 8 to the power of x plus 27 to the power of x, I can plug this in. So then it becomes a to the power of 3 plus b to the power of 3 divided by. Instead of 12 to the power of x plus 18 to the power of x, I can plug this in. So this becomes a squared b plus ab squared. And on the right hand side, I have 7 over 6. Yes. But then you realize that we have a factorization, yes, for this one and this one. We can factorize and simplify this left fraction more, yes. I can write as this is the sum of two complete cubes. So the answer is the cubic root of the first one times the cubic root of the second one. And then I will have the first one to the 2 minus 2, the first one times the second one, and the second one to the 2 divided by. I factor ab out, then I am left with a plus b. On the right hand side, I have 6 plus 7. So what I do here now, I can see that this factor and that factor can be cancelled. So what is left for me in the numerator is, this is negative, ab plus b squared divided by ab. And this is equal to 7, 6. So by the zero product rule, I will see that I will multiply 6 by that, and then I will multiply 7 by this. So I will get 6a squared minus 6ab plus 6b squared is equal to 7ab. So if I move 7ab to the left, then it becomes 6a squared minus 13ab plus 6b squared is equal to 0. Okay, but this can be actually factorized. So this can be factorized here. So how? If I want to factorize this, I would write it in this form. I would write it as 6a squared. Instead of 13ab, I would write 9ab minus 4ab. Yes, and then I will have 6b squared is equal to 0. So then I can take these two together. I can take these two together, this one and this one, and I can take these two together. If I do that, then what happens? I can factor 3a out from the first one. It is left, the first one is 2a minus 3b. And if I pull out minus 2b from the second one, it becomes 2a minus 3b. Yes, that's a successful factorization. Yes, because now you can see that 2a minus 3b can be pulled out, and then I am left with 3a minus 2b. b equals to 0. So there are two possibilities. Either 2a is equal to 3b, or 3a is equal to 2b. These are two cases. Yes. Okay. Now let me write everything here in front of your eyes. So what happens if I have 2a equals to 3b? What was a? Do you remember a little bit here? Yes. So a was this expression and b was this expression. 2 times a means 2 times this expression. So it becomes 2 to the power of x plus 1 is equal to 3 times b means 3 times this expression. It becomes 3 to the power of x plus 1. But then you see that on the left hand side you have a power of 2, the base is 2. On the right hand side you have a power in base 3. This cannot happen unless this common number is indeed 0. Yes, so then it implies that x plus 1 is 0. Then it implies that x is equal to -1, and that is one of those answers that you were looking for. Do you remember? We were supposed to solve this equation. Okay? But there is also another possibility, and this one is this possibility. So let me write it here again. 3a is supposed to be equal to 2b, but let us see what happens. A is 2 to the power of x. So you now multiply it by 3. So what happens? It becomes 3 times 2 to the power of x. And on the right hand side you have 2 times b. b is 3 to the power of x, and then you multiply it by 2. So it becomes 2 times 3 to the power of x. Okay? Now what we can do? We can do it like this. Here I conclude that 2 to the power of x divided by 3 to the power of x is 2 over 3. Yes? It's clear, yes? Because if I do the cross product, 3 will be multiplied by 2 to the power of x, and then 2 will be multiplied by 3 to the power of x. So this, what I have written here, is completely correct, because if I do the cross product I will get this expression back. Okay? But why I did this? Because it's helpful. Instead of 2 to the power of x divided by 3 to the power of x, I can write 2/3 to the power of x. And on the right hand side I have 2/3. 2/3 means 2/3 to the power of 1. And now compare these two. There are two powers with the same base. They are supposed to be equal. So it means that this can happen if and only if the powers, the exponents, are equal. So it means that x is equal to 1. And then you see that there are two answers. Either x is equal to -1 or x is equal to 1 are the possible answers for this problem, for this equation. Yes. Okay, so I hope that the video was useful for you. If that's the case, I would appreciate it if you can give me a thumb up. And then if you want to be notified as soon as I upload a video, I would appreciate if you could also subscribe to my channel. Okay? Until the next video, okay, goodbye.